Hi, everybody. This time we're going to talk about energy that is released from chemical bonds, and this energy is stored in fuels. Now, the amount of energy that is stored in a chemical fuel in a bond is really well known and can be calculated very, very carefully. All of these chemical fuels that we've been talking about are hydrocarbons. And when they chemically react with oxygen and produce carbon dioxide, water vapor, they give off energy as heat and light. This is all part of that law of conservation of energy, can't be created or destroyed, just simply changes forms. Where did that energy come from in the first place? Well, it's from the sun. Years and years, millions of years of photosynthesis has fixed that carbon dioxide and water into those hydrocarbons that is stored underground in those fossil fuels. Well, this bond energy, the exact amount of energy that is stored in individual bonds, has been determined by chemists that are older, wiser, and have more experience than you and I. And there are charts that you can examine and look at, and they know exactly how much energy is in a carbon-hydrogen bond, a carbon-nitrogen bond, a silicon-hydrogen bond. And this is a partial chart, and there are other charts that are out there. But armed with this sort of information, you can truly calculate exactly how much energy is going to be released if a chemical compound is fully and completely combusted. So let's do this. Let's calculate how much chemical energy is going to be released when methane, a methane molecule, is burned. Now, this can also be referred to as bond enthalpies, and the energy we are going to calculate is going to be in kilojoules per mole. Now, what we have here is a methane molecule, and a methane molecule is a carbon, and it is surrounded by 1, 2, 3, 4 hydrogens. So there are 1, 2, 3, 4 carbon-hydrogen bonds. So if I take one carbon-hydrogen bond is 413 kilojoules, kilojoules per mole, and I have 4 of those for each one of these bonds right here. And when it is fully combusted, that is totally eliminated and all that energy is released. So 4 of those is going to be 1,652 kilojoules of energy per mole of methane is actually released. Now, what does that mean? Well, that is a number that is an indicator of how much heat and light can be released by the combustion of methane. But you can use that same process for more complicated compounds. So let's take a look at octane. Octane as in the octane rating of gasoline. So if we look at this, octane, it contains 1, 2, 3, 4, 5, 6, 7 carbon-carbon bonds. So we're going to have 7 carbon-carbon bonds, and each carbon-carbon bond from right here is 348 kilojoules per mole. So we take 348 kilojoules per mole, and that's going to be 2,436, and I did my math earlier, so let's hope I wrote it down correctly. And we also have, and I'm going to switch colors so this is a little bit easier to see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 carbon-hydrogen bonds. So we have 18 carbon-hydrogen bonds. So we have 18 of these. Each carbon-hydrogen is 413 of those kilojoules per mole. And if I grab a calculator, that ends up being 7,434. Oh, I didn't write that pretty. Let's try that again. 7,434. If I add these two numbers together, I end up with 9,870 kilojoules per mole. So the wonderful thing is when a new molecule is constructed, you can actually do the math and figure out how much energy is released. So here's what I'm going to ask you to do. Hit pause, Try doing this for yourself. Take a look at a small molecule like propane. Can you calculate the amount of energy that would be released if propane was totally, all of the bonds were broken? Okay, hit pause, give it a try. All right, let's go through this. I've got 2 carbon-carbon bonds, 2 carbon-carbons. So this is going to be 2 times 348. So 2 times 348 is going to be 696. And I have 1, 2, 3, 4, 5, 6, 7, 8 times carbon-hydrogen bonds. So 8 times 413. So 8 times 413 is 3,304. Add both of those together, and I got exactly, hope I didn't hit the wrong buttons in my calculator, exactly 4,000 kilojoules per mole. Pretty nifty stuff, and very neat that you can calculate that pretty simply. Here's the big idea I want you to understand. I want you to understand that as we go through from short chain hydrocarbons up here with methane, ethane, and propane, through the mid-chain hydrocarbons, octane, kerosene, and diesel, and we get to the longer chain hydrocarbons, as the molecule gets larger and larger and larger, what that means is the longer the chain of the hydrocarbon, the more energy is going to be released when that compound is burned. So what does that mean for you and I? Well, what that means is if you are going to do something like boil a pot of water on a stove, methane, ethane, propane, these are fine. If you're going to light a cigarette, butane's fine. You don't need a high-powered molecule. If you are going to try and run your automobile, you want a fuel that's going to be potent enough that you're going to pack a lot of energy in a small space. If you're going to try and run bigger vehicles like jets or big diesel trucks or big diesel trains, you are going to need large molecules so that there is a lot of energy in each one of those molecules, and so you are going to need a much more potent and powerful fuel. Potent, powerful, and energy-packed fuel is going to be meaning a long-chain hydrocarbon. Little mini methanes, great for boiling water and frying an egg, but you need a big engine with a lot of power to haul an 18-wheeler down the road. All right, that will do for this time, and we'll see you next time. Bye-bye.